It is mathematically impossible to perfectly tune a piano. Let's see why. Here are some common intervals and their frequency ratios. An octave has a frequency ratio of 1 to 2. For example, the note A3 and the next A above that, A4, have the frequencies of 220 Hz and 440 Hz. They are in a 1 to 2 ratio, and it's a similar idea with the others. Now, on a piano, it is impossible for all of these ratios and more to be satisfied at the same time. Here's why. Let's compare an octave to a perfect fifth. Now, I'm going to rewrite the 2 to 3 ratio as a 1 to 3 halves ratio by dividing both quantities by 2. Now, for an octave, it takes 12 half steps to get from one note to the other. And with a perfect fifth, it takes 7 half steps to get from one note to the other. If you're not familiar with music terminology, a half step is just getting from one key to the next one.
So C to C is an octave. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we have a perfect fifth over here, C to G. We have 1, 2, 3, 4, 5, 6, 7.
Now, the least common multiple of 12 and 7 is 84. So if I go up an octave 7 times, or a perfect fifth 12 times from the same note, that frequency should match. Let's see if it does. Now, it doesn't matter what the original frequency is. We just care if the multipliers are the same. So let's talk about an octave. Well, 12 times 7 is 84, so we're going to multiply by 2 7 times. And for a perfect fifth, well, 7 times 12 is 84, so we are going to multiply by 3 halves 12 times. So let's see if these are equal. And with the calculator, we see that these are not equal. Now let's do this again, but comparing an octave to a perfect fourth. So we have a 1 to 2 ratio and a 3 to 4 ratio, which I'm going to rewrite as a 1 to 4/3 ratio. Once again, an octave has 12 half steps going from one note to the other, while a perfect fourth has 5 half steps going from one note to the other.
C to F is an example of a perfect fourth. 1, 2, 3, 4, 5.
Now, the least common multiple of 12 and 5 is 60, so we can check in 60 half steps if their frequencies match. So that's the same thing as going up an octave 5 times, or going up a perfect fourth 12 times. Let's see if these match. And they do not. And by the way, this doesn't work for any of the intervals. So how would a piano tuner tune a piano? Well, a lot of them do it by equal temperament, where each half step up, they would multiply by the 12th root of 2. But why the 12th root of 2? Well, they tune them by the octaves, and octaves have a frequency ratio of 1 to 2, and there are 12 half steps to go from one note to the other. So if we want 12 of the same number multiplied together to get 2, what would that number be? That would be the 12th root of 2. Now, because of this, no other interval besides the octave will be perfect, because we keep multiplying by irrational numbers, and all of those other ideal frequency ratios are in whole number to whole number ratios. So no other interval besides the octave will be perfect, as we see over here. So there you have it. That is how we can show mathematically why it's impossible to perfectly tune a piano.